Okay, so now let's see, like, why. So, what have we done so far? We looked at the problem in one dimension. We developed a test for certificates in, one-dimensional mixture of K-Gaussians. And then, we argued the completeness and soundness of the test. Okay, that's what we've done so far. And now, I want to tell you why what we did so far would imply an algorithm. Oh, actually, I should remind you also, we formalized the notion of complexity of proofs, the sum of squares proofs, and we observed that under that notion of complexity, the argument we did over there, which I will let it remain for a while on the right side of the board, was degree t squared. Okay, and t would be a small parameter eventually, like log k. So eventually, we are shooting, for complexity of that sort. We'll see how it soon relates to algorithms. Okay. So that's what we have done so far, and now we want to look at how to get algorithms. Okay, good. So we already saw one very inefficient algorithm, right? The very inefficient algorithm was go over all possible sets of size n over k. Okay, then apply the test. You know that only true clusters will pass the test, pass the test, and every fake cluster will fail it. So, after you just go over all possible n over k of, you basically have approximately the clustering of the data points. So, this immediately gives you like a 2 to the n time algorithm, right? We want to now, develop an efficient one, but before we do that, we'll develop an even more inefficient algorithm. Okay, so we'll make it worse before it gets better. Okay, so the even more inefficient algorithm would look like the following. This algorithm will find a probability distribution D over W that satisfies the two requirements in the test. Okay, so the test is written over there. This algorithm finds, a distribution over W. So W is in, remember, 0, 1 to the n. So it's a distribution on the n-dimensional hypercube. And the support of the distribution should be all overall W that satisfy the two constraints here. The first one, remember, is sum Wi equals n over k. And the second one is like whatever is the encoding of this inequality as a polynomial inequality in W. Okay. By the way, just to remind you, I'm still designing an algorithm for clustering a one-dimensional mixture. I'll come back and tell you how to get high dimensions later. Okay. Good. So that's, you find a probability distribution, and then what? What should you do if I have a distribution like this? Well, it's not clear what finding a distribution means, because how are you representing it? It in principle seems like a distribution over 2 to the n things. So a distribution over 2 to the n things in principle requires like doubly exponentially many parameters to write down. And let's say you wrote it down, okay, whatever, who cares? Okay, so you have like that cumbersome a description of this distribution D, we are looking at it. But if you have this distribution in some form, what should you do to actually get a clustering? You just sample from it, right? We argued the correctness property, right? Like if W satisfies the test, it has to be close to a true cluster. So if I sample from this distribution, I will basically get true clusters, okay? So this is like a algorithm that definitely works. It's highly inefficient, but it works. Okay, so now let's understand, let's think at least for a few seconds about this algorithm. Now, it works in the sense that it will give you at least one true cluster. But the distribution it finds could be, for all we know, it could just be supported on the first cluster. Right? It may not give you information about the second cluster or the third or the kth cluster, right? Because so far we just asked the algorithm to find me a probability distribution, which is supported on W's that satisfies the test. So first cluster satisfies the check, so it can give you just first cluster all the time with probability 1. The point is that if it did this, then this distribution is not enough to give you information about all the k clusters. So I have to somehow augment this algorithm, or I have to like restrict it further, the type of distribution it gives me, in order to get information about all the k clusters. Okay, so I'm going to force an additional constraint that under this distribution, the expectation of all the wi's should be equal and equal to 1 in k. Okay? Now, first of all, notice that there is such a distribution, right? It's not like I'm asking an impossible task here. Why is there such a distribution? The uniform distribution on the true clusters is in particular going to satisfy this check, right? Satisfy this constraint. But you should more or less think of it as like, I want like a completely spread out distribution. I don't want you to ignore any point. I know every point occurs in like a cluster. So give me a distribution where the expectation of every point is in fact like as small as it possibly could be. Okay? You're trying to make the distribution behave like the uniform distribution on the k clusters, if you will. Does this make sense? Now notice that, if I did get such a distribution and I sampled about like k log k times from it, then by coupon collector you will see all the k clusters, right? Sounds reasonable? Okay, good. So yeah, this is the highly inefficient algorithm that we have designed after a lot of effort. It doesn't seem such a great idea. I'll come back and say, by the way, but right now I'll just tell you a buzzword to remember this idea by. This is an instantiation of an idea which is actually very useful in general. It's the idea of imposing maximum entropy objective. Like in many situations, you are interested in not just finding any solution, but completely spread out solutions for various reasons. And this is an instantiation of that idea, okay? Yeah, that's all I'll say about it. Okay, so now, we got a super inefficient algorithm. Let's make it a little bit better, okay? Right now, we don't even have, certainly we don't know a way to find as a distribution, but moreover, we don't even know how to write down this distribution in a small number of parameters, okay? So let's try to cure this property, this problem. Let's try to, at least ask for an object that can be described by a small number of parameters, okay? So what we'll do is, I'll replace this step by a 2 prime and show you how you can actually extract clusters by looking at only low degree moments of the distribution D. Okay? If I can do this, then I at least have solved one problem. I can write down this object in at most D to the 2t different real parameters, right? Because I just have to, in order to run this algorithm, I don't actually have to find a distribution which is supported on W satisfying the test. I just have to find the first 2t moments of this distribution. There are D to the 2t numbers that describe all the first 2t numbers, namely like the monomial moments, right? And so, at least I can describe this object in a small number of parameters. Does it make sense? Okay, so let me give you this algorithm, and then, we'll continue to make it better. Okay, good. So, okay, good. So, let me show you how to round, in fact, using just first 2 moments. We'll need to extract 2t moments for some other reason, but actually I'll show you how to round using just first 2 moments right now, okay? So here's the observation, here's the key observation. Since D is supported on solutions to the test equations, test constraints, and since every point in the support, every point W in the support satisfies the conclusion that we proved. Right? Because, I guess the statement is now erased, the proof remains, but you can reconstruct the statement for the proof. We know that sum of Wi squared is supposed to be 0.99 on any W that satisfies the constraints of the test. D is supported on only such W's. So it must be true that every point in the support satisfies this. In particular, it must hold that if I take the expectation of some Wi squared, I should get at least 0.99. Yes? Good. So let's like draw this, because this has a nice picture meaning. Okay? Let's look at the matrix where so there is like a one row and one column for every one of the sample points. So it's like 1, 2 up to n, and the ijth entry is simply expectation under D of Wi times Wj. Okay. Now let's arrange the points. Like we don't know this rearrangement, but for the sake of like analysis, assume that the first n over k points was the first true cluster, and the next n over k points was the next true cluster, and so on. Okay, so the clusters basically are like diagonal blocks right here. Okay, so let me erase this again now. Okay, this is how the cluster looks, right? N over k by n over k, that's like the first cluster, and so on. Okay, still with me? This inequality, or actually like its implication for like the cross terms, means that if I add up all the terms here and the terms here, then the sum of all these entries of this matrix must be at most 0.01. You all agree with this? That's basically what we proved over there. Okay, like WR times WR prime is basically the product up to normalization. It's the product of all those WIs which lie in like WI WJs, where I is in the Rth cluster and J is in R prime cluster, right? So what we proved over there is that okay, so there is this, I guess, some normalization issue I'm missing. Sorry, let me just see. Yeah, I guess I should. Maybe the right way to think about it is like sum. Yeah, I think let's look at the case where like the sum is 1. So like normalize it. Like let's look at like 1 in n square times sum w. Like then I think this description I'm saying makes sense. Like then I think what we proved over there means that all these off diagonal entries, they sum up to at most 0.01, and so these diagonal blocks sum up to 0.99. Okay, which is kind of nice if you think about it. What we are saying is this matrix has positive entries. Why does it have positive entries? Because every point in the support is non-negative, so its expectation must be non-negative. So I have a bunch of positive numbers that add up to 1, right? But outside of the diagonal blocks, the contribution is at most 0.01. And the diagonal blocks are basically what I'm interested in finding. So what we're observing is that this matrix is approximately block diagonal, and the blocks are precisely the clusters we are looking at. Okay? Notice that this matrix is a function of just second moments of the distribution D. So I'm using only the second moments of the distribution D to look at this matrix now, right? So how do I get it? From here, I claim that it's very easy to recover the clusters approximately. How should I do it? Yeah, that would be, but it's like something much more trivial works. Guess a random row and take the large entries in that row. If you guessed it here, the large entries will be here, right? And do it like whatever k log k times. You will hit like an entry in each of these blocks, and that's it. Okay, does it make sense? Now you do require, for this to succeed, you do require that there was substantial mass in every one of the diagonal blocks. Okay, but that is true because we know that the expectation of Wi is 1 in k. Okay, like we force this constraint. Okay, this constraint implies that there is good mass in every one of these, and so yeah. So I won't be like too descriptive about this detail here, but basically like a very simple algorithm works, which is to just write down the second moments. It has this approximately block diagonal structure. You just like repeat k log k times, guess a random row, take the largest k n over k entries in that row, and that's your guess for the corresponding cluster. It does make sense. Yeah, you're all good? Okay, good. So we've done something nice in the sense that at least we know how to round the round given like second moments of an actual distribution, right? Yeah. Yeah. Yeah, you can do that. And that will also work here. So indeed, like in this particular application, you didn't necessarily need to, put the max entropy constraints in there. Instead, you can iterate and all. You would still like argue that this is simpler. But actually, the max entropy turns out to be useful in some situations where this iteration is no longer possible. So there are like slightly tougher versions of these questions which go by the name of list decodable learning. And then it turns out that in some sense, this max entropy things are actually crucial. You can't just get away with iterating there. Okay. So like the reason I like it is because it makes it simple here, but in other applications it is crucial. Does it make sense? Crucial. Okay, good. Anyway, any other questions so far? Good. Okay. Good. So now what I want to show you is how to get an efficient algorithm out of this whole business. So why is this not efficient, by the way? Because computing a distribution supported on solutions of the test is in general hard. Okay. At the highest level, if you're trying to find a distribution supported on solutions, you're solving polynomial equations, and that's an NP-hard problem. But more, perhaps like more importantly, solving this test is more or less the same as like solving the clustering problem. And so if you knew how to find a distribution supported on clusters, why would you do all of this discussion to begin with, right? So far, this is not helpful. But the idea now is going to be that we will find an object. This object will be called a pseudo distribution, which will have the same relevant properties. So what are the relevant properties of this that we use? Well, we use that this distribution has moments, the first low order moments, like first moment, second moment, and so on. And the second moment had the property we cared about, right? Like the second moment had a bunch of properties that we used in this argument. What were the properties? The properties were like that the entries of this matrix are non-negative, that they sum up to 1 if I scale by 1 over n square, and that the diagonal blocks basically contribute 99% of the mass, right? These were the properties we used. I'll now show you that there is a different object called a pseudo distribution, which will have the same properties, by virtue of which the same rounding algorithm will continue to work. This same algorithm to extract clusters will work. But importantly, unlike a distribution, a pseudo distribution satisfying the requirements of the test would in fact be efficiently computable. Okay, so that's basically the final punchline of the algorithm. That's how we get the algorithm. Okay, does the idea make sense? Does the plan make sense? So I'm going to describe like this relaxation of distributions. So, okay, so this object I'm going to define now is called pseudo distribution. So say D is a pseudo distribution it has a notion of complexity just like sum of squares proof. So it's a pseudo distribution of degree h on variables w1 up to wn if 1, the expectation under this pseudo distribution it happens. So okay, so sorry, let me maybe let me maybe define it a little bit better. So a pseudo distribution D is a linear operator that maps degree up to h polynomials into real numbers. So this degree h is like how many moments of this pseudo distribution I can actually compute. So it is a degree up to h pseudo distribution such that one, the number, and I'm going to call these the numbers that it gives to polynomials, and in general numbers that it gives to monomials, I'm going to call its moments, okay? Just by analogy with the actual distributions, okay? Right now I've not told you what this object at all is. It's just a linear operator. It gives like numbers to monomials. Linearity means that if I take any polynomial, then the value it will get will be the appropriate linear combination of the values I give to monomials. So, that's all the definition is, but I'll continue to use the notation as if it was a distribution because, we can maintain the analogy to the argument on the left-hand side. So the expectation of the all ones function, which is a degree 0 monomial, would be 1. This is true for actual distributions, and we are saying that, this property is going to be reflected in a pseudo distribution. And, more importantly, expectation of every square polynomial would be non-negative if the polynomial f has degree at most h over 2. Okay, so I'm only allowed to compute degree up to h moments because for this object I only have definitions of degree up to h moments. If you give me a polynomial whose square is of degree at most h, then for such a square my expectation under this pseudo distribution would always be non-negative. Okay, does the definition make sense? Let me say some things about it in order to help understand it. If I take, notice that an actual distribution in particular is a pseudo distribution of degree infinity because I can compute expectations of all polynomials. And in particular, if I take expectation of a function which is non-negative everywhere, then the expectation will necessarily be non-negative. Right? Since a square is non-negative everywhere, the expectation of a square will always be non-negative. So any actual distribution will definitely satisfy these two properties, right? But this in particular is a restriction of it. There are two ways in which this definition is a restriction. One is that it only applies to low degree polynomials. It only applies to polynomials of degree up to h, right? I'm not claiming anything about degree beyond h. But moreover, this object cannot reason about non-negativity. It does not know about the non-negativity of functions which are non-negative everywhere but may not be squares or sum of squares, right? The only kind of non-negativity it can reason about is non-negativity of squares. Okay? So in that sense, it is like a weaker object. Okay? It satisfies weaker constraints and therefore it's a more general object, right? Like there are many more pseudo distributions and distributions, if you will. Okay, good. Now, yeah, I'll further say that D satisfies a constraint a polynomial constraint p equals 0 if for every p prime, every polynomial p prime, such that the degree of p prime plus degree of p is at most h, expectation under D of p times p prime is 0. Okay, this degree condition is simply saying that I should not compute the expectation of anything which is a degree bigger than h polynomial. So this is like, it looks cumbersome, but it's nothing. Okay, it's saying that, look at what happens for actual distributions and actual expectations. If I have a polynomial which is 0 and my distribution is supported on solutions to p equals 0, if I take any polynomial p prime and compute the expectation of p times p prime, because on every point in the support p is 0, this function is identically 0 on the support of the distribution, so this expectation will be 0, right? We're saying that the same property we're going to use as the definition of what it means for a pseudo distribution to satisfy a constraint. Does it make sense? Yeah. So these are all my time-saving measures where I'm not saying some things, but okay, let me say it given that you brought it up now. So you can think of yeah, so let's answer Santosh's question. Maybe it's actually even helpful to understand what's going on. You can think of a pseudo distribution D as a map from, let's say, Rn to real numbers, okay? And then you can say that, you can define expectation under this map of any polynomial P as simply, let's say it's finitely supported because I don't want to write integrals. X such that dx is non-zero, d of x times p of x. Okay, this is like definition of what expectation under D means, right? And then, what I wrote down is basically like some properties of this function D, okay? This property, for example, means that sum of dx is 1, right? Like that's what this property means, right? This property means that sum over x dx fx square is always non-negative if f is a low degree polynomial. Okay, you're all good with this, right? And like Santosh said, an actual distribution has some property which is obvious, which is that dx is always non-negative. Okay, it's a density or like mass function, right? I'm not claiming that, and in fact, it won't be true in general. So you can think of a pseudo distribution as relaxing the non-negativity of the mass function, okay, while still maintaining like a few consequences of that non-negativity. Okay, good. I think I know what you're talking about, but no. You can think of this as more like a sign measure. Oh, I see. Okay, then yeah, sure. Yes. Yeah, so they're sign measures. I mean, they're just literally, yeah. They're literally like arbitrary functions which satisfy these two properties.
So for example, the derivative operator corresponds to a distribution, but it won't be a sign measure because like taking two delta functions and the opposite.
Yeah, okay, I know what you're talking about. So you're worried about like, spiky things, right? Like you're saying if it's a delta function. Sure, yeah. So they're representable measures. Like, yeah, I suppose functional analysts will say that I should be able to apply the Rees representation theorem and like obtain a sign measure like this to write down the corresponding expectation. But right, that's the reason I want to just work with finitely supported things so that I don't get into formal issues. For finitely supported things, these are all, yeah, they're all the same. So it's just a finitely supported sign measure. Okay, good. So the most important fact about pseudo distributions is that they are efficiently computable. Actually, maybe I'll make two observations. One, our rounding works for any degree 2t pseudo distribution that satisfies test conditions as constraints. Okay, so let me say what this means. So, this definition tells you what it means to satisfy a constraint, a polynomial equality constraint. I told you to think of inequalities as also equalities by adding slack variables, so I'll continue to do that. So now, we observed before that these are polynomial equalities in W variables, right? Like this one quite trivially is, this one also is, and I can write it down, if you wish. It's like this one is k over n, some I from 1 to n, wi, xi minus like this polynomial to the whatever t is at most 1.1 e to the t over 2, right? Like the point is that this is a polynomial of degree t plus 1 in W, right? So both of them are polynomial inequalities. So imagine that, I found a pseudo distribution that satisfies these two constraints in W, okay, and is of degree at least 2t. Then I want to claim that, I can look at the first two moments of this pseudo distribution, repeat this argument, and it will succeed, okay? So when I argue by just like, saying words why this is true, okay? first notice, so what do I actually have to prove? I have like the moments of this pseudo distribution. All I have to argue is that this pseudo distribution satisfies this property. Right? Actually, I also have to prove that it satisfies non-negativity. So let's maybe start there. I want to prove that the entries of this matrix are non-negative under a pseudo distribution. Why is it true that ED, WI, WJ is non-negative? You can only use the definitions on the board. Okay? So you observe that WI and WJ are indicator variables. So in particular, WI is WI squared and WJ is WJ squared. So ED, WI, WJ is ED, WI squared, WJ squared, which is another square. And by 2 here, it's the square of a degree 2 polynomial. So if I have at least a degree 4 pseudo distribution, its expectation must be non-negative.
Why is it degree? You have to do something about like multiply 1 minus xi or something.
Sorry, what?
So it's an indicator function if I want to.
WI indicator just means that WI takes the value 0 or 1.
Yeah, that's fine. But it's so I think I'm confused about what is it a polynomial over? Oh,
over the
entries
W.
Over the entries of W. So then it's
It's a polynomial in W. W is our indeterminate. So actually that reminded me that I should write down that WIs are indicators as constraints explicitly. So actually there are more constraints. There were 2 of them here, and then we were implicitly using it, but we didn't say it like WIs had to be 0 or 1 valued. So those are also thankfully polynomial constraints. That's fine. I just throw it in there. Okay. So now if I find a pseudo distribution that satisfies these constraints, then we've argued by property 2 that all the entries of this guy are non-negative. Right? By a similar thing, you can argue that they must sum up to exactly 1. Why is that? Why should the entries of this matrix sum up to exactly 1? Yeah, and like importantly, it satisfies 1. Okay, because it satisfies 1, sum WI is n over k. Okay, because sum WI is n over k, you can show that sum WI squared should be n squared over k squared. Okay, and then by satisfying constraints, that the expectation of sum WI the whole square should be n squared over k squared, and we normalize it. So that's it. Okay. So anyway, those were the simple ones. The hard one or the interesting one is, why is this true? Okay, because we proved this by that elaborate argument over there. So we have to now argue that somehow this property 2 implies that even for a pseudo distribution, this same inequality holds. Okay, so let's try to look at this argument. We proved that some WR times WR prime is at most some constant over here. Okay, but we observed that this was a sum of squares proof. Okay, so in particular, we know that what we proved here can be written as 0.01 minus R not equal to R prime WR prime is some sum of squares polynomial in W plus something in the ideal generated by the constraints. Like it's some polynomial combination of the constraints, right? That's what it means to be a constraint sum of squares proof. That's what we argued in the last last of the lecture, right? Okay, so now this argument, what we did, basically implies that there is an identity of this sort. Importantly, you can extract this SOSW explicitly if you can, but we don't need to. Okay, this is a feature that we don't need. Like, we know it exists, we don't need to extract it. But now I claim you are done. Why? We know this identity holds true. This is the sum of squares. Okay, what is the degree of the sum of squares polynomials? We know it's at most t squared. Okay, because we argued that the degree of this proof is at most t squared. So if the pseudo distribution is of degree at least t squared, then that square that appears on the right hand side must get a non-negative expectation. And therefore, we can rearrange and get that this cross terms must add up to small. So therefore, that inequality must hold.
Well, I mean, the ideal is also of small degree. Because
Yes.
Summing up to a small.
Yes, yeah.
And that is
So degree being t square means that every polynomial that is part of the proof, so that every sum of squares and including the multipliers in the ideal, they're all of degree at most 2t. Yeah. Good. Do you all see this? So the point is that we did some abstract nonsense at this point, right? Like, none of this is like, I'm not even writing down, but the reason I'm not writing down is because it's abstract nonsense, okay? I'm saying that, I just wrote down this condition, okay? It looks like a weak condition, but it's not. We just made a proof, we use like non-negativity of squares there, and then we just like use the fact that, this condition can help us basically recover the consequences, okay? So I'll state the conclusion in words, okay? We only checked it for like this specific example, but here is the underlying principle. If W satisfies a bunch of constraints, and any W satisfying this constraint, suppose in low degree sum of squares implies a new inequality on W is satisfied, just like what we did. Suppose the degree of the sum of squares proof of this inequality is some number, whatever, t squared in our case. Then a pseudo distribution of degree at least that number will basically follow the consequences, follow this inequality that actually we derived as if it was an actual distribution. So for the purpose of facts which are provable using low degree sum of squares, a pseudo distribution behaves like an actual distribution. Okay? Sounds all right? So what have we done? We've just discovered that if I could argue, and actually, okay. I haven't argued to you why this object is efficiently computable, why a pseudo distribution is efficiently computable. I'll actually give that argument in 5 minutes to you. But modulo that, we've at least completed the 1D algorithm. You all see this? Right? If I argue now that a degree t squared pseudo distribution can be computed in like some reasonable amount of time, then we know that we can basically run the algorithm. What will we do? We'll find a pseudo distribution that satisfies the constraints of this test of degree at least t squared. We'll take the first two moments of this pseudo distribution. We'll do this simple rounding where we guess a row, take the large entries, and we have the clusters for us. Okay? So let's see why a pseudo distribution is efficiently computable. Yeah, okay. Okay, so before like people find it objectionable, let me say that I'm lying a little bit. There are some numerical issues I'm going to sweep under the rug for the purpose of this talk. Okay, if you are bothered by it, or if you want to ask me what they are, ask me after the talk. But right now I'm going to just pretend that this theorem is true and tell you why it's true. Okay, so let me argue why, if you want to find a degree t distribution, degree t pseudo distribution, satisfying a bunch of polynomial constraints, m different polynomial constraints, in n variables can be found in time mn to the order of t. Okay. So let's see the proof. The proof is simply that a pseudo distribution that satisfies a bunch of constraints can be written as solution to a semi-definite programming relaxation. Okay. So eventually I showed you that SDP at the in the beginning of like the last lecture, that SDP was simply computing the pseudo distribution. That's all it was. Okay. So we'll write it as an SDP. Okay, so what will be the variables of this SDP? Well, a pseudo distribution like this can be described by its moments, right? So the variables will be the values for the moments. So, we are, let's say, in order to keep things simple, let's say that, we are always working with hypercube today. So Wi square is Wi for every I. Then, I only need to describe multilinear moments. Right? So W sub S means the product of Wi's where I is in S. Okay? So these are all, if I have a distribution which is supported on the hypercube, these are all the moments. If I have like more general things, I have to take like, powers of individual variables. This just allows me some notational simplicity. Okay? You still with me? So these are my variables. If I want to compute a pseudo distribution of degree 2t, I need to give you values for this. And these are enough. That's all I want to compute. Okay? Now, for these values, I'm going to write down the so-called moment matrix, which, is going to be indexed by subsets of size at most t over 2. Okay, and the entry at S comma t is going to be the expectation of Ws times Wt, or the moment at S union t. Okay, so this I'm just going to call the moment matrix. This is the definition. Okay, so I'll be a little bit quick here, but the key observation is that if I want to compute the expectation of a square polynomial f of degree at most t over 2, okay? So let's say, my polynomial looks like this. F is some s such that s is at most t over 2, some coefficient times the monomial w, right? That's how any degree t over 2 polynomial looks, right? And let's say I want to compute expectation of this square. Then the observation is that this is simply a quadratic form of this matrix M. Okay, so that's the key observation, that expectations of squares of polynomials are quadratic forms of the moment matrix. Okay, and this you can compute. This is just like direct computation. There is no mystery here. Okay, why does this help? This helps because the non-negativity of all squares is if and only if all the quadratic forms of M are non-negative, which happens if and only if M is positive semi-definite. Okay? So all I've done here is observe that this condition, that expectation of squares is non-negative, is equivalent to taking these numbers that describe the pseudo distribution, putting them in a matrix, and observing or confirming that this matrix is positive semi-definite. Okay? So why does this help? It's like, I want to compute a pseudo distribution, so I want to compute these numbers, and we've just observed that I can encode these infinitely many constraints of non-negativity of squares as a one positive semi-definiteness constraint. Okay? And then, you can see that satisfying the constraints is a bunch of linear constraints on M. I won't write it down, like it's a bunch of linear constraints in these variables. Okay, I won't write it down here. So the observation, this whole discussion means that the task of finding a pseudo distribution that satisfies a bunch of constraints is basically same as the problem of finding a bunch of numbers which satisfies some linear equations. And in addition, when you put these numbers into a matrix, the matrix is positive semi-definite. Okay? Such a system of constraints where there is a positive semi-definite constraint is a convex program, and in particular, it is an example of a semi-definite program. A semi-definite program is basically exactly this object, satisfying a bunch of linear constraints on a matrix which is positive semi-definite. It turns out that you can efficiently solve it. And again, like there are numerical details asterisk here, which I'm sweeping under the rug for now. But basically, that's the reason why a pseudo distribution of degree t satisfying a bunch of constraints can be computed in the time which is polynomial in the size of the object you're computing, right? Because it's an SDP of some size, and I'm just like applying a polynomial time algorithm for solving an SDP, which we know exists. Okay? Good. So that's it. I've described to you how to solve the one-dimensional mixture of Gaussians problem in about 2 hours. This one? Yeah. So first notice that, so even though I want to enforce this on all p prime, it's enough to enforce it on p prime that are monomials, right? And so then there are only d to the 2t or n to the 2t different monomials, right?
There are linear constraints.
Yeah, there are n, so this corresponds to n to the 2t different linear constraints, right? So it's like polynomially many linear constraints on the entries of this matrix. Yeah, feel free to ask more questions. Yeah, because I'm going to launch into the hand wavy part of the talk from now. So
the test constraints are written out with the ED applied.
No, what do you mean?
And the WIs are not variables.
WIs are variables. I mean, in the SDP, the variables are the expectations of products of Ws. What does it mean to written out? Yeah, so let's maybe answer that question too. What does it mean? Well, I want to satisfy this as a constraint, which means that I need to enforce for all p prime times n over k minus some Wi is 0. So that's what I'll do. Yeah. Feel free to ask more questions if there are. Yeah.
So the rounding algorithm use only the first.
Yes.
But satisfy these higher order.
Yeah. So why? So maybe you can tell me why I needed the degree 2t pseudo 2t square pseudo distribution. Yeah, no. In the test constraint, how many constraints are satisfied is up to me. But the key inequality I needed in the analysis was something that is erased now. The key inequality was like, sum of Wi squared, the expectation should be at least 0.99, right? The proof of that inequality required higher degree polynomials. So even though the rounding algorithm only needs degree 2, that argument requires higher degree. Yeah, any other questions? Good. So this is much ado for nothing in some sense because we solve a 1D problem. But now let me explain to you in a very hand wavy way why like not much needs to be done for the higher dimensional problem. Okay. So first, let's talk about like how to change the test for higher dimensions. Okay. So if x's are high dimensional, then these are vectors, right? And so what does it mean to take moments of vectors? Well, I actually want to take moments of projection of these vectors in all possible directions. So this constraint I'm going to replace by and just for the sake of normalization. Okay. So now I have an inequality, one for every direction. So let me write down for all V in RD. Okay. So now I have infinitely many inequality constraints. Let's continue to work with it. Okay. That's my test constraints now. Now we have to worry about, remember how we started. We first give an identifiability proof, then we go back and try to make it an algorithm. Okay. So we don't know how to check these constraints. Unlike the previous one, it's not clear how to check this because there are infinitely many constraints of them, right? But let's continue with it for a second. Suppose I want to show that any W that satisfies this test constraint must actually also have that property that, like the moment matrix, the second moment matrix should be approximately block diagonal. How should I do that? Well, I'll be a little bit hand wavy, but the point is that the same argument works. Okay, that's the reason I did not erase it all this time. So what would I do? Well, I'll do this argument after projecting all the vectors into a fixed direction V. Then it's a 1D problem. Okay. So, this first step, okay, so let's ignore the first step. We'll get back to the first step later. But let's say you were bounding this, like let's say you came till here somehow. And you have projections of mu r star and mu r prime star into V. Okay. So this expression is now mu r star V minus mu r prime star V whole to the 2t. Okay. Then if you continue on, nothing changes because from here on it's a 1D problem. 1D problem of mixture of k Gaussians in direction V. everything else continues. You get all the way up to here, okay? And yeah, in fact, you get all the way up to, yeah, I guess you get all the way to the end. What you're missing is like the link between the expression you want and this expression, right? Because delta is the L2 distance, L2 separation between the means. But I'm now arguing something about an arbitrary direction, right? I need not have separation in that direction. The key observation is that if I fix a pair, the L2 distance is witnessed by a single direction, namely the direction of the line joining the two means, right? So for any fixed pair, I can take that direction and I'll have delta, right? Like this is true. Then this inequality is true. In general, for every pair, there is one direction. So there are k square many directions, right? So in this inequality, if I have to like replace it by some expression like this, I'll take the k square directions, take the difference in those k square directions, and then I can write down this inequality. Because I know that for every pair, there is some direction that witnesses it, okay? Now I do the whole thing, but I'm bounding k square direction. So at the end, I'll have some extra k square term, so I'll get a k cube thing. That's it. Yeah. Because it is one term that, gets me. Yeah, so that's it. That's the high dimensional proof, okay? And I literally told you the whole proof. I'm not hiding any detail here. Okay, this is it. I can write it down, but it's easier not to. Do you have a question, Jatin? Okay, good. So that's the high dimensional proof. So what have we done? We proved that the same condition holds if we can somehow encode these tests, okay? So now let's go to the whole algorithm part. We have to now find a pseudo distribution satisfying this bunch of constraints, but we are now in trouble. If I try to write them down as a constraint, I have an SDP with like infinitely many constraints ostensibly, but even if you are clever and discretize it, it's like 2 to the d constraints. Which covariance matrix? This is the degree 2t polynomial. You're almost there. That's a very good idea, okay? And so let me say Jatin's observation, because it's a good observation, and then we'll see why it's important. Jatin is trying to say that even though there are infinitely many constraints here, there is a way to compress it down, okay? And his observation is the following. Suppose t is 1. T is 1, then this is a quadratic inequality, okay? This is saying that x minus mu c v square should be small. It's equivalent to operator norm of x minus mu c transposed being small. Okay? I'm getting there. In general, this is not possible to do for higher moments. Okay? Not even with tensor products. Why not? So in some sense, it's a higher degree polynomial inequality. I'm saying like, for quadratic, it is a testable condition, but you should not expect this condition to be testable in general. Because, it's a polynomial optimization problem. Like checking this is like, certifying optimality or like maxima of a certain polynomial of degree 2t. This is an NP-hard problem, right? So you should not expect this inequality to be testable beyond t equals 1. Okay, do you all like roughly see this? Like, quadratic optimization is easy, but quadratic optimization is NP-hard. Okay? Does it make sense, Jatin? Okay? So how will we succeed? I still want to compress the constraint. I still want to follow Jatin's idea. How should I do this? Well, here's the key observation, which I will not justify all that much right now. This is a polynomial inequality in V. Okay? If this polynomial inequality has a sum of squares proof of low degree, then I claim that you can write it as an operator norm condition on some bigger matrix. Okay? And the idea is that, you make it an identity. Like that's the whole business here. You can always make inequalities into identities if there are sum of squares proofs. Identities means that I can write this down as plus some sum of squares of V equals the right hand side. Okay? And now, you can almost immediately see why you should expect compression. If this SOS in V was explicit, then this is just like a matching coefficient conditions on both sides, because that's how polynomials over the reals behave. And there are only like, d to the 2t, n to the 2t coefficients. Okay. But actually, you don't even need to know SOSV. You basically, you can write SOSV as I'll be a little bit sketchy here, but you don't even need to know what this SOSV is. You first make variables for this SOSV, whatever this SOS polynomial is. Then you write down the coefficient matching constraints, which are linear constraints, and you force SOSness of V by an SDP very similar to this argument that we did here. Okay, so the point is that if there is a low degree sum of squares proof of this inequality, of this sub-Gaussianity inequality, then you can impose these constraints, efficiently. Okay, I'm going to call this low degree sum of squares proof property for whatever distributions you can hope to do this. I'm going to call it certifiable sub-Gaussianity. Okay, so this property that we needed in order to at least write down the SDP that makes sense, I'm going to call certifiable sub-Gaussianity. And then, whatever we did is true for any distribution that satisfies this property. Okay, so I'll just make one simple observation which will handle Gaussians, and then everything else I'll say it out loud. Okay, I claim that Gaussians are certifiably sub-Gaussian. Okay, let me prove that to you. Here is a fact about Gaussians. If X is a standard Gaussian, then the point I'm trying to make is that the moment inequality we wrote is actually an equality. It's already an identity for Gaussians. So we are done. Right? Like SOSV is 0. Or if you will, if you want like this 1.1, then SOSV is a constant polynomial. A non-negative, in fact, a strictly positive constant, which is a sum of squares polynomial in V of degree 0. Okay? So Gaussians are certifiably sub-Gaussian. But actually, you can show more. So at the time, we could prove that if distributions satisfy a Poincare inequality, then they are sub-Gaussian. If this KLS conjecture is true, which Santosh will tell you about tomorrow, a little bit, I'm promised, then actually the same result implies that every log concave distribution is certifiably sub-Gaussian. In fact, like it's kind of very surprising, and Santosh will probably mention this question. Even though we know the truth of this based on a conjecture, people will believe is true, we should expect a direct proof because it's such a simple statement and we don't know our proofs yet. Like I was telling you, more generally we know, or like, somewhat incomparable we know as of this year, or as of a few months ago, that every sub-Gaussian distribution is actually certifiably sub-Gaussian. So, we can write down an SDP like this for, clustering mixtures of any sub-Gaussian distribution. Right. So KLS conjecture implies that all log concave distributions satisfy a Poincare inequality with dimension-free constant. The latter statement, what we showed that any distribution that satisfies a Poincare inequality with dimension-free constant must be certifiably sub-Gaussian, meaning it must satisfy this inequality with a sum of squares proof. In fact, sum of squares proof of degree 2t. So, if the KLS conjecture is true, then every log concave distribution is 2t certifiably sub-Gaussian. So we don't know that true. That's a KLS conjecture. KLS conjecture says that every log concave distribution satisfies a Poincare inequality with dimension-free constant. Yeah. So okay. Okay, I understand the confusion. So you're saying, So when I mean certifiably sub-Gaussian, or like certifiably sub-exponential, probably is a better name. All I mean is that the relevant inequality has a sum of squares proof. Sorry for being a little bit So you're right that it's not be t to the t, it will be t to the 2t. That's what you're concerned about, right? For log concave distribution, I won't satisfy. They're not sub-Gaussian, but they are sub-exponential. So I will satisfy this moment growth with like t to the 2t and not t to the t. Sure, but I'm saying that, I'll still have a sum of squares proof of this, is the point. Like that. So what we proved is that, whatever is the truth, it can be certified by a sum of squares proof. Separately, for all sub-Gaussian distributions, we know the same is true now. So what we did now actually holds for if the KLS conjecture is true, then what I showed you today actually allows you to cluster mixtures of arbitrary log concave or arbitrary sub-Gaussian distributions. Okay, good. So let me, just summarize and end. I guess I'm not going to tell you about non-spherical mixtures at all, so there'll be no geometry.
One question. So this is for the distribution, right? Whereas that is for the samples.
Yeah, excellent question. Yeah, I was hoping somebody will not ask me this, but yeah. So there is a calculus of certifiable sub-Gaussianity, and where you show that all of the relevant things you believe that you would like to be true are true. For example, samples of sub-Gaussian distributions, certifiably sub-Gaussian distributions are certifiably sub-Gaussian. Differences are certifiably sub-Gaussian, shifts are certifiably sub-Gaussians, linear transformations are certifiably sub-Gaussian. You can basically show that, natural operations that you do on a distribution that will maintain sub-Gaussianity actually also maintain certifiable sub-Gaussianity. This is a little bit like, Prasad's talk, where you want to have like some kind of sanity check kind of results that, some natural properties that hold for stationary distributions or stationarity, whatever, should also hold for local stationarity. It's the same analog. You have to do that and it's done. So yes, it's true that this property is closed under sampling. So if the distribution is certifiably sub-Gaussian, then so is like an empirical distribution on large enough sample from it. Yeah, the number of samples has to be whatever is required for the moments to converge in Frobenius norm. So it's d to the 2t. You can be a little bit clever and make it spectral norm, but yeah, d to the 2t. Good. Any other questions before I summarize? Okay, summary time. So, I told you like, one application. Apologies to many people because this application is really dated now. It just shows my age. This application is whatever, 7+ years old. No, Prasad is unconvinced. It doesn't show my age apparently. But I thought like it's a nice example because it illustrates a lot of like ideas. Like one is that it's not a bogus application. It's a problem that people cared about. So even if you don't care about sum of squares, you hopefully learn something about a problem that is not so boring. In the context of sum of squares, it shows you why the task that you had to do to design this algorithm was just one lemma. The one lemma was the soundness analysis of your test. Okay, and how did we do it? It's not like we were like holding ourselves back all that much. We did an argument that is maybe not so far from an argument that you would naturally do, arguably, if I asked you to do it without any sum of squares constraints. Like you had to prove some inequality. It's like yeah, go crazy on it, and like you'll probably do some of the manipulations I did. Perhaps you'll be tighter or whatever. Maybe you'll not use silly triangle inequality, but you'll use triangle inequality instead. Fine. Up to those considerations, you will probably do the same kind of argument. And the point is that the argument you would do, the natural argument I wrote on the board over, it already is sum of squares, and further to prove it is sum of squares is also easy. We did exactly 2 applications. Both the applications were applications of this silly triangle inequality. That has sum of squares proof, and then we apply composition theorem. That's it. Okay, so the point is the algorithm design task, if you know all the rest of the black box background material, is just proving soundness of the test. And as long as you can prove the soundness of the test with like simple inequalities. Today I used only silly triangle. Sometimes you use Cauchy-Schwarz or like some relevant related things like that. But the point is that these inequalities are actually more powerful than they might appear. Many of the arguments that we do actually only use them. And so you are already giving sum of squares proofs of like relevant inequalities already, and you might as well design algorithms with them. So anyway, like all the long list of applications I showed you in the previous version of the talk, previous part of the talk, were basically obtained exactly by this way. Right? Like just giving explicit sum of squares proofs like this, and just applying this black box machine to design an algorithm. Cool. Okay, I'll stop here.